Today in class 11th, I will tell you some examples of conservation of mechanical energy. I told you in the previous lecture the conservation of mechanical energy. Now there are two examples which are in your course and also they are asked in your final exam of the 11th class. So one is the freely falling bodies and second the particle executing SHM. So I am taking the first example. Conservation of energy of a freely falling body. This is now first example. So now let us take, this is the ground. Here is the body. This is at point A. Now height of this point A from the ground is h. Now this body passes through a number of points while falling freely. Let here we are having another point B. This is a distance x from A, and now this will be distance h minus x from the ground. Here this body is falling freely, so its initial velocity is equal to 0. Let here is the velocity of v1 and here the velocity is v2. So when the body falls from height h, it passes through a number of points. So we are considering only the 3 points A, B and last this point C. If the conservation of the mechanical energy is followed at these points A, B, C, then we can say that this is true for all points through which it passes. So there is the conservation of mechanical energy. So now let's M equal to mass of body. Now body is falling freely under the gravitational field, and you know that the gravitational field is the conservation field. The body is falling freely in gravitational field. Which is conservation field. Conservative field. So now at point A, the potential energy U equal to mg h. This we know. And the kinetic energy K is equal to half m, and now speed is equal to 0 here. So this is equal to 0. So total energy E equal to K plus U. K is equal to 0, U equal to mgh. So we get this E equal to mgh. Now total energy at the point A is equal to mgh. It means that at the point B and C, the total energy must be equal to mgh. Only then we can say that there is the conservation of mechanical energy. At point B. Now when this force from point A to point B, it has travelled a distance x. So it will gain some velocity v1, and the potential energy of this body will be equal to potential energy U equal to mg h minus x, because now the height of this object at point B is h minus x from the ground. Always remember that whenever we are finding the gravitational potential energy, height is always measured from the ground. Now velocity v1. So this will apply using third equation of motion. This is now your v square equal to u square plus 2as, and here is what? This u equal to 0, v equal to v1, and this a equal to g, and s equal to x. So now I put all these values in this equation, and we will get this v square equal to 0 plus 2gx. So this v1 square equal to 2gx. Therefore the kinetic energy, this k equal to half m v1 square. So this is equal to half m, and v1 is equal to 2gx. This 2 and 2 will cancel. So this k equal to mgx. So now you see that the potential energy has decreased, because here it was mgh and this is now mgh minus x. The kinetic energy has increased. Here the kinetic energy is 0, but at the point B the kinetic energy is mgh. So kinetic energy has increased from 0 to mgx. So total energy is how much? Total energy E equal to K plus U. Now then you sum this K mgx and U equal to mgh minus x. So now you can see that this E equal to, this is now K is equal to mgx, this is mg into h minus x, so this is mgx plus mgh minus mgx. Now these will cancel, so E equal to mgh. So again we find that at the point B, the total energy is mgh, while at the point A this was also mgh. So at point A and B, this law of conservation of mechanical energy is followed by the body. Now at point C, now the potential energy U equal to mg. This is now 0. So this U is equal to 0. Because when the body has reached at the ground, the height from the ground is 0. So the potential energy is 0. Now the kinetic energy. Now velocity V2. Again we using third equation of motion. We have this v square equal to u square plus 2as, and here this u is equal to 0, v equal to v2, and a equal to g, s, this is equal to h. So this v2 square equal to 0 plus 2g, and this is now h. So v2 square equal to 2gh. This will give you the velocity. And now find the kinetic energy. So kinetic energy K equal to half m v2 square. This is equal to half m v2 equal to 2gh. 2 and 2 will cancel. So this is equal to mgh. This is equal to K. So now total energy is how much? Total energy E equal to K plus U. So this E is equal to K is equal to 0, K is equal to mgh. mgh and U is equal to 0. So E equal to mgh. This shows that at the point C, it means that on the ground the total energy is again equal to mgh. So this treatment shows that when the body falls freely under gravity, the mechanical energy is conserved, or the sum of kinetic energy and potential energy remains the constant. It proves that the body falling freely under gravity follows law of conservation of mechanical energy. Mechanical energy, it means the sum of kinetic energy and potential energy remains constant. Here we consider that there is no friction due to air. due to air is neglected. So the body is falling under the gravity under the gravitational field of the earth. So in that case, the sum of the potential energy and the kinetic energy is constant. This is the first example of the law of conservation of mechanical energy. Now the second example. Now second example. Conservation of energy of a body executing SHM. So now what we have, that let a body of mass M executes SHM with amplitude A. So now what we have, let this is now position of the body. This is the mean position. This is the position A and this is now position B. This is the amplitude A. This is amplitude A. Now let the body is at any time here. This is now suppose a point, we take it to be now C. So that this distance is X. So body is going from here in this way and then coming back, and then this is going in this way and then coming back. So the particle is executing SHM about the mean position O. The potential energy of body, this U is equal to half k x square at the point C, because C the displacement is x. At point C, and the kinetic energy. Now this kinetic energy equal to half mv square, and this is equal to half m, and v is equal to omega square root of a square minus x square. This is now whole square. Here this v is equal to omega square root of a square minus x square. So this is equal to half m omega square into a square minus x square. Now this square root will cancel. So kinetic energy is equal to half k into a square minus x square, where k equal to m omega square. Omega, the angular frequency or the angular velocity. Omega equal to angular velocity. So now we have the sum of the total energy is how much? Total energy E equal to this kinetic energy plus the potential energy. So E is equal to half k a square minus x square plus half k x square. So now we take this simplified to this one, half k a square minus half k x square plus half k x square. These terms will cancel. So E equal to half k a square. This is so much. And you see that this total energy is independent of the displacement x. And A, that is the amplitude which is constant, K is also constant, so E is equal to constant. The total energy is independent of displacement x. So this energy is constant. So total energy is constant. So now from this equation that we have this half k a square minus x square and half k x square, and you can see from this expression and to this expression that when the particle goes from mean position to point A or A to O and then O to B and B to O, what happens? When the particle is going from mean position to the extreme points A and B, its velocity decreases because x increases. So kinetic energy will decrease, it means the potential energy will increase. When the particle is coming back towards the mean position, then the kinetic energy is increasing because x will decrease. This x will decrease. So this kinetic energy will increase and the potential energy will decrease. So the sum of these two again will remain the same. It shows that when the particle executes SHM, its total energy is always conserved. Thus, total energy of body executing simple harmonic motion is conserved. We can show it by a graph also. This is a graph that will show you the conservation of energy. This is the point. This is now your maximum displacement. Here this is now x equal to 0. This is now opposition. Here is x equal to minus a, and at this point we are having this x equal to plus a. So this shows the potential energy of the particle, and then the same time we are having the this. So this is for potential energy, and this is for kinetic energy. This shows you the total energy, E. So what we have, that when we are going from x to this point, this is the point A that I have taken to this one, point A, and this is now point B. So when we are going from O to A, then read this graph. The x, the potential energy is increasing, and this graph is going like this way to kinetic energy decreasing. And when we are coming back, then the graph is repeated in this way. So this potential energy decreases, but kinetic energy increases. This is the graph is coming like this one. Similarly, on this O to B. So when the particle executes SHM, the total energy of the particle is always constant. So this is the conservation of mechanical energy of the particle executing SHM. So these are the two examples which are in your syllabus, and they are also asked in the your final exam. So thank you very much.